Our speaker for the next talk is Ilan Schnell, and he's going to talk about Conda, the cross-platform package management system for any binary distribution. He works at, he's involved with continuum analytics, and welcome everyone.
Oh, could I have some water?
Of course.
Okay, thank you. So, welcome everyone. My name is Ilan Schnell, and there has been quite a buzz at this conference about Conda, and I want to explain a little bit more how Conda works and what it does. There's a similar talk to this one that my colleague Aaron Moira actually gave at SciPy 2 weeks ago in Austin, Texas. And the title of the talk is Conda, a cross-platform package manager for any binary distribution. And that's the official talk, and the unofficial talk is solving the packaging problem. So, what is the packaging problem? So, in the Python community, there has been a long history. A lot of things have happened to try and solve this problem. There was, of course, distutils first of all, and then Philip Eby started the setup tools project, and then Tarek forked it into the distribute project, and then it got distribute got merged back into setup tools again, and now we have pip and wheel formats. But yeah, unfortunately, I don't think that any of these attempts from the Python community itself are able to solve the fundamental packaging problem, and this is why Conda takes a quite different approach to packaging. So, in packaging and distribution, there are really two sides of the problem. You have the problem of installing packages and building packages. And users only usually want to install packages, whereas the developers, they build packages, but developers are also users, so they also install packages. And Conda tries to make this distinction very very distinct, the side of building and the side of installing. And the interface is really the Conda package format. And the Conda package format is really extremely simple. And that's important because when you have a simple format, you have a simple interface between these two aspects, the installing and the building of packages aspect. So, how do you install Python packages currently? There are many different ways to do that. ZPY install, easy install, which is deprecated. Now people use pip. There's also system level packages like apt-get, RPM, and some others. Python setup.py install works fine if it's pure Python, and if it's not pure Python, things need to get compiled, and often you get these cryptic error messages that you might not have GCC installed, or even if you have GCC installed, you might get some errors about some header files being missing on your system. And then you might have to install some RPM and to Python setup py install again. Basically, when you use Python setup py install, you are your own package manager. And yeah, pip really only calls out to Python setup py install. Pip only works with Python, and it's not so great for scientific packages that depend on big C libraries, as such as HDF5. So when you try to install pip install h5py and you don't have the HDF5 dependency installed, which is a C system level package, then you have a problem. Nick Coughlin from the Python Packaging Authority really says that when you're using pip, you are a self-integrator. Yeah, here's some of the history with building Python packages. Some of the problems, I mean, the root problem really, in my point of view, starts with distutils. It wasn't really designed for compiled packages, and that's the reason why NumPy forked distutils, but NumPy distutils comes with its own problems. Then setup tools is really over-engineered and very complicated, and there's a lot of, I would say, evil things, like it monkey patches distutils, and you have problems with entry points, and another thing is that it wants to install everything into either eggs or into egg directories, and that's the reason why you have this easyinstall.pth file, which adds all these eggs or egg directories to your sys.path. And this code here is actually code from the easyinstall.pth file, which exposes it exposes the fact that in a pth file in Python, which is used to add other directories to the module search path, you can have actually an import statement. And if one line in that pth file starts with import, then Python executes that code. And well, I think it's bad that Python really allows a hook like this in pth files, but it's even worse, I think, that that setup tool now exposes this hack and builds all its machinery around it. So package maintainers hate having packages that no one can install. So I've been talking about the packaging problem in Python so far, but I think the real problem is this one. So what about wheels? Well, and the reason, obviously, is that most of the developers develop their packages on either Mac or on Linux, and there aren't, I mean, if I just look at the people in this room, I see many MacBooks, and people have accounts on Linux servers, and if I look at the company I work for, we have really only 2 people that know Windows very well, and everyone else is working on Unix systems. So that's, yeah, a challenge. And on the other hand, most of the users of Anaconda, for example, are Windows users. We have between 60 and 70% downloads for Windows. So how about wheels? Don't wheels solve this packaging problem? Well, not really. You can't build C libraries as wheel packages. You can't build the HDF5 library, the Atlas library, VTK, all these NetCDF, all these C-level libraries. And you cannot create a wheel package of Python itself. Wheel is really like a different version of these egg packages that are installed into the side packages. They're purely designed around, centered around Python itself. Also, wheels don't address the metadata problem, which is that on the server, you don't have all the information you need to install a package and install its dependencies as well. On the PyPI server, there is an XML RPC API that you can call from Python, and it will tell you what packages are available, and you can query metadata about those packages. But one important thing that is missing is the dependency of those packages. And that's the reason why pip, when it installs something, it has to download your package, extract it in a temporary location, then it looks at the setup.py for requirements, and then it installs these downloads and installs these other packages as well. And Conda does this differently, as we will see later. It has a full index of all packages with all its dependencies. So really you are still a self-integrator if you use wheel packages as well. There are system packaging solutions. Linux, we have yum, apt-get. There are some on OS X, Windows, but they are all different, and you don't really want to use a different tool for all these different operating systems. And Conda was designed to be cross-platform from the beginning. It's a single code base for all OSs, and I've learned at this conference there are some other tools that have similar goals, like the source PKG project, but I think that's limited to Unix. It's not? Okay. And also the Nix packaging solution. But yeah. So, what is Conda, and how is Conda trying to solve this problem? Conda is a system-level package manager. It's Python agnostic, and the reason that I think the Python community is struggling with packaging, and has been struggling with packaging for such a long time, and well, is still struggling. And I don't think that the current attempts with the wheel format are going to solve these problems. Is that they treat Python like the operating system. So you have Python installed, that's like their assumption, and then you do everything on top of that. But Conda is really going one step back and saying, well, you really have to treat everything on the same level, whether it's Python itself, whether it's an HDF5 C library or a Python package like H5Py. These are all Conda packages, and Conda treats all of these the same way. And yeah, this allows you to have much more flexibility. You can, for example, with Conda, install Python itself, and you can install different versions of Python, Python 2.6, 2.7, Python 3, and so on. Python is cross-platform. Well, Conda is cross-platform. It doesn't require administrator privileges, and it installs only binaries, and metadata is stored in a separate file on the repository index, and it uses a set solver to resolve these dependencies before anything is installed. I have a question. So how many people in this room have already used Conda? Okay, maybe half. So maybe I can show some demos later how you actually use Conda, but the people that use it, they will know that when you install something with Conda, it first fetches some index files, then it tells you these packages are going to be downloaded, these packages are going to be linked, and then installed. So everything that's going to happen is known a priori because of this index file. So here are some of the basic usage commands. You can install list packages, you can search for packages, you can create environments. I haven't mentioned environments yet, but these Conda environments, it's really like an install prefix with different things in it. Like, for example, the user directory on a Linux machine is one prefix, or user local is another prefix. And you can create such prefixes, such environments in your home directory as well. And yeah, that's what usually happens when you say Conda create, and you can give names to these environments, and also, but you can also give it the full prefix, and then you can specify packages you want to have there, like Python 3 or Python 2, or be more specific about the version, and then install things into that prefix. Yeah. And you can always get help by using the -h option on all the Conda subcommands. I was surprised a few days ago at the conference that someone was struggling with Conda, and it turned out they didn't know about the -h. The online documentation is not always up to date, but the help files, the help text, that is kept very up to date because it's right there in the source. And yeah, you can install packages into specific environments, you can update environments, you can actually export a list of packages in an environment, and it writes it, you can just pipe the output to a file, and then you can, on a different machine, install all the packages that are listed in that file. You can, in each environment, Conda keeps track of all the changes you're doing, and you can list the revisions and the changes that have been done by all Conda commands, and then you can revert back to older revisions. So I've been talking about the Conda package format. So what does it look like? So a Conda package is a tarball, a bzipped tarball, and it follows this convention here about the file name. It has the package name, the version, and a build string, and well, the tar.bz2 extension. And inside that tarball is the whatever you install with that package. You have the lib directory, the include, bin, man, share directory, whatever, and then there's a special file, well, a special directory with two files, with the files file, which lists which files are going to be installed, and the index.json file. That file is used for the repository index to extract information about the package. This file format is not Python specific, and the metadata is static, and it's important to point out that you can quite easily actually create these Conda packages with simple tools like like tar, basically. I mean, we have this tool called Conda build, and it has a lot of features, and it helps you build Conda packages in a systematic way, but it's not really the only way you can build these packages. Yeah, everything is Python agnostic. A Conda package can really be anything. It can be Python itself. In Anaconda, we support Python 2.6, 2.7, 3.3, 3.4, and also recently Python 1.0. There's a Conda package. Actually, there are three Conda packages, two for Linux, 32 and 64-bit, and one for OS X with Python 1.0. And C libraries, R libraries, the R programming language, we have built Conda packages for that. Node.js, one contributor has built some Conda packages for Perl, like Perl itself, but then also Perl extensions, and yeah, you can do that for Julia, whatever you like, you name it. Okay. What happens actually during the installation process of a Conda package? So well, the first thing that happens is that Conda looks at the repository data, figures out what dependencies there are, what needs to be installed, and then it downloads the tarball, it untars it in a packages directory that's a cache, and then files a hard link to the install path. And I'll talk about that in a minute, but the reason for hard linking into the install path is to save disk space if you have many different environments. And once things are hard linked into the install prefix, then there are some little changes like to the shebang line and other things that are done with the installed package, and it also allows to run post-install scripts. It's like a bash script you can run after the install, but none of that is Python specific. And finally, the metadata. is updated so that Conda knows something has been installed. Yeah, and that's it. It's really a simple process, the installing of Conda packages. We always try to keep all the complexity on the building side and have the format and the install process as simple as possible. Okay, I've talked about environments a little bit. So one thing to mention here is that these environments are really completely independent installations of everything. And to allow that to be possible, you need to be able to create relocatable binaries. And by relocatable, I don't mean that you can just take your install prefix and move it somewhere else. That wouldn't work because of the things that happen during the install process, like rewriting the shebang lines. But by that, I mean the Conda package itself needs to be written in a relocatable way. So the way we do that with the linking is that we use like on Linux, the origin in the R path, and there are similar tricks on Mac and on Windows we use as well. And, well, most important of all, you don't have to set the Python path or LD library path. You don't have to fiddle with any of these things. All you really have to do is add that new environment or the bin directory of that new environment to your path. And that's not really necessary either, because you can just execute binaries in any environment directly if you specify the full path. So here's an example. We have two environments here, one called test and one SymPy environment. And in both environments, Python 3.4.1 is linked to, but only in the SymPy environment, SymPy itself is linked to. And yeah, on the left side, you have the package cache. This is where everything is extracted. And doing it this way, you see that Python is actually only extracted once. It saves disk space this way. And however, I mean, these environments also work on like cross-file systems, but it might fall back to creating either symbolic links or copies. And hard links actually also work on Windows, even on Windows XP. So, yeah, it's also memory disk space efficient on Windows. But we had to do some tricks to make that actually happen on Windows. The os.link function out of the box in Python doesn't work on Windows. So environments, they can be used to test different Python versions. And actually these Python versions are only the ones that are supported in our like official Anaconda repositories. You can like build your own Conda packages for like Python 2.4 or 2.5, whatever you like. And you can use these environments for development. You can try out new packages from PyPy. If you create an environment, you can install pip into the environment, and yeah, then you can pip install into these environments as well. And yeah, ultimately we want to make science more reproducible by having these reproducible environments. Okay, I want to talk a little bit about building. So Conda comes with an extension called Conda Build. It's a separate package that you install with Conda, but it's all part of the Anaconda distribution. But if you start from Mini Conda, Mini Conda is this installation that has only Conda and the dependencies of Conda, and if you start from there, then you would have to say Conda install Conda build, and then you have the Conda build command available. And what it does, it creates a Conda package from a recipe, or actually it creates several Conda packages from one recipe, and you can specify whether you want to build a package for one version of Python or another version. And obviously, if you run that recipe on a different architecture like Windows, then it will create a Conda package for Windows. And in this Conda recipe, you have metadata, and you have build scripts that tell you how things are, what steps are actually need to be executed during the build, and you can apply patch files to your source, and you can specify some tests as well. And it's really a framework for building these packages. So what Conda build does, it looks at your recipe and then it provides the source for you. It extracts the source and sets up a build environment. It runs the script, and then all new files that get installed into that build prefix, they get packaged up into the Conda package, and then things are tested. Okay. I think, how are we doing on time? Okay. Maybe it's best to actually show how you would build a Conda package. And so I'm here. Is this readable? Well, I can actually make it larger. So I have a recipe here for M4, the macro language. So in this recipe, it says package is M4, this version. This is where the source is coming from. And for test, I just run these commands. And the build script says configure, make install, and the prefix is going to be the prefix where things get installed to. So I just run Conda build, and I give it the directory of this recipe. And now it's building M4 for the Mac. And I chose this example actually because it's not a Python package. In a Python package in the recipe, instead of configure, make install, you would say something like Python setup py install. And you would also have dependencies. You would have Python as a build and a runtime dependency. In this example, it's much easier because there are no dependencies at all. We just rely on the system GCC and the system C runtime as well. Okay, so it built the Conda package for M4, and now I'm going to upload this to Binstar. Binstar is this hosting service for packages. So this is my account here, and there's no M4 here yet, but now I will say upload this package. It's going to upload the package I just built. I'm going to refresh this page, and here's M4. And if I look at files, there's only one file here for OS X 64-bit. And now if I say Conda install channel Ilan M4, it will download M4 from Binstar and link it. Well, it actually didn't download it now because it was probably already in the cache. That's actually right. I have to make sure that you actually see the whole thing. So suppose we're on a different machine, which doesn't have the package already built, then it would download it. Well, now it's already installed, so I have to say Conda remove M4. Okay. Now it's actually downloading the package. It's downloading it, it's extracting it into the package cache, and then it's linking it, and M4 version, yeah, that's the M4 that comes from the Conda package. Okay. What else do I have here? Yeah, this is basically sharing packages with Binstar, and as you might notice, this is actually an Emacs package, a Conda package for Emacs that my colleague Aaron has created in his account. You can also self-host Conda packages. You just create a directory with then subdirectories for the different architectures, and then you run the Conda index command in these subdirectories. And if we have enough time, which we might not, I could do a quick demo of how that's done. So I create a directory, PyData 2014, and now I create a directory OS X 64. I go into that directory, I copy the Conda package of M4 into that directory. Now I run the Conda index command. Now you see these repo data.json file here, and now I go one directory up, and this needs to be served, and we have a web server in Python already. We just say python-m simple HTTP server. And now it's serving. Now I say, well, now I have to, in my Conda RC file, add this local repository to the channel list. Now I can say Conda search M4. And here it is, and it comes from localhost. And you can see here that there was a request made to the server. So it's really nice to be able to create a repository of packages with a static web server. With PI, this is not possible. You have to have some application running on your web server. Okay, yeah. Conda is completely open source. It's BSD licensed. It has a mailing list, conda@continuum.io. I would like to take this opportunity to thank Continuum for paying me to do work on this open source project. And thanks to these people, especially Aaron, who is now the principal Conda developer, Brian van der Ven, who is the co-author of Conda, Sean, who is the developer of binstar.org, and Travis Oliphant, who is the CEO of Continuum. And thank you for using Anaconda and for your attention.
Thank you for the nice overview and good, let's say, very informative demos. As they say, actions speak louder than words, so those were very useful. So we have time for one quick question.
Are there any plans to address the problem of cross-compilation of the packages? So I have, for example, a Mac OS X machine, and I want to generate packages for Windows, Linux, and Mac OS X. Is there any way I can do it now, or any plans in the future to implement that?
Well, the packages if they are pure Python packages, your Mac package will be the same as the Linux package, and on Windows, because the directory structure is a bit different, we have a tool called Conda Convert, where you can convert this into a Windows package. But in general, as soon as you have C extensions, this wouldn't work anymore. You have to really compile or cross-compile if that's possible. Okay.
One more question. Can you tell us a little bit about the vision that you have with Conda? Because my feeling is that it's very accepted and people really like it in the science and data community.
Yeah.
But outside of that, it's not. This my feeling. It's not that much used. So, are you approaching that, or what is?
Well, I mean, it's really two things. I mean, there's Conda, but there's also Anaconda, the collection of packages that we from Continuum maintain and keep up to date and make sure they work together. And those are packages for the scientific data Python community. So, I mean, if other people would have equally well-tested things for other domains, then Conda would be probably more accepted in those domains as well.
Thank you very much. I'm afraid we have time for no more questions. So let's thank the speaker once again.